Hey, what is up everyone? I hope all of you are doing great, and I welcome you all to our new lecture series of simple harmonic motion. And this video and or this series is totally focused for IIT JEE or JEE Advanced recently, as you know. So if you are an IIT aspirant, you should stay tuned to this channel. If you are not subscribed yet, do subscribe the channel and please press the notification bell icon so that you don't miss any of our videos. Okay, so without wasting any much of your time, let us start our topic of simple harmonic motion. Simple harmonic motion is one of those topics which can be connected with any other chapters also, like work, power, energy, kinematics, Newton's laws of motion, or you can say electrostatics. You can name anyone, rotational mechanics, fine. So it is one of the most fundamental chapters, and it is a very interesting one also. To start with simple harmonic motion, you need to be familiar with three types of motion. First one is periodic motion. Second one would be oscillatory motion. And third one is our simple harmonic motion. Okay, so what is periodic motion? Periodic motion are generally those type of motions which repeat themselves after a fixed interval of time. Repeats themselves after a fixed interval of time. Okay, so basically motion of the moon around the earth, motion of the earth around the sun, motion of the electron around the nucleus, these all represents a type of periodic motion. Okay, but you cannot say that these are simple harmonic motions, because simple harmonic motions comes under their own category and under their own constraints. Okay, so oscillatory motion. What is oscillatory motion? Oscillatory motion are kind of periodic motion, but they prefer the to and fro type of motion. Okay, like simple pendulum, fine. So oscillatory motion are generally to and fro kind of motion. They are also periodic motions, but they prefer this to and fro type of nature, like a simple pendulum or a spring block system, you can say. So what is simple harmonic motion? Simple harmonic motion is basically the subset of an oscillatory motion, that these are also to and fro motion but of small amplitudes. Okay, so figuratively you can say that simple harmonic motion falls under the subset of periodic motion as well as oscillatory motion. So these are also to and fro motion but with small amplitudes. Okay, so this is you can consider simple pendulum, motion of a simple pendulum, as SHM, but the angular displacement of the simple pendulum won't be much. It would be nearly 4 degree. Okay. Okay, so this one was the basic introduction of simple harmonic motion, but this one is just a qualitative information. We would jump into the mathematics right now. So if you want to just subjectify the whole oscillatory and simple harmonic motion in a mathematical sense, you need to say that as you can understand that for to and fro motion there must be a restoring force. What kind of force? A restoring force. That for any type of to and fro motion there must be a mean position. There must be a mean position, and whenever the particle moves away from the mean position, the force will bring back that particle to the mean position. Okay, so a restoring force is necessary for the to and fro motion of a particle, and this restoring force must vary like this. where n must range from n must be an odd number. Okay, so the restoring force acting on a particle must vary with the displacement, where x is the displacement from the mean position to the power n, where n is 1, 3, 5, 7 or any odd number. Okay, so if this kind of type of force acts on a particle, then the motion would be oscillatory, and if n is equal to 1, then f will be minus x. So if this kind of force acts on a particle, the motion of the particle will be a simple harmonic motion. Okay, so this special type of force must act on a particle to perform simple harmonic motion. As you can see that higher order variations are not included here, only the first order is taken. So as I have said that SHM is nothing but an oscillatory motion with small amplitude, so restoring force does not vary in higher orders with displacement. Okay, so F is directly proportional to negative displacement. If you remove the proportionality term, you put a constant in the equation, and this K is famously known as SHM constant. Okay, the dimension of K is Newton per meter. Fine. Okay, so let us understand again. So there is a mean position. Whenever the particle displaces away from the mean position, a restoring force starts acting on the particle, so that it tries to bring that particle towards the mean position. Fine. So let m be the mass of the particle. So you can write F equals mass into acceleration equals to minus kx. So acceleration is minus k by m times x. Okay, so a equals minus omega square x, where omega equals root over k by m, which in future we will call this one as angular frequency. What? Angular frequency, having a unit of radians per second. As you can see that we have considered root over k by m as omega. We could have taken some other power also. We could have taken omega to the power 3, omega to the power 5 or anything, but that would make the final solution a lot uglier. So omega square keeps the final solution of this differential equation, or in future we will get a differential equation. That final solution would look good. Okay, nothing else. Anyways, as you can see that the acceleration is basically variable. It varies with the displacement of the particle. So variable acceleration, we just need to study the motion of the particle, that how it changes, how the position of the particle changes with time for this kind of acceleration. Right? So it is basically kinematics and nothing else. So let us continue further, but before solving the mathematics here, let us study the motion once again. So if this line is the mean position line and this one is the path. Okay, so this one is the mean position. Let the particle start from the mean position with an initial velocity v0 towards the right. Whenever I am throwing the particle towards right with a speed v0, the displacement of the particle starts increasing. Okay, because the particle starts moving towards right, so x is increasing towards the positive axis or in the positive direction. So the acceleration starts acting towards left, so the acceleration increases and the velocity or the speed decreases. Okay, so the particle moves towards right. At some point of time, the velocity of the particle will become 0. Okay, and at this point the acceleration is maximum, and it tries to pull back the particle towards the mean position in this direction. Okay, so this position is known as the amplitude. means the maximum displacement from the mean position is known as the amplitude. Okay, now the acceleration pulls back the particle towards the mean position again, and in this situation or in this motion, the acceleration decreases because x decreases and the speed increases. Okay, so the acceleration is pulling back the particle towards the mean position, increasing the speed, and with time the acceleration is also decreasing, but again the particle comes at the mean position. Speed of the particle is same as initially, but in the opposite direction. The particle moves further till a location x equals minus a, and again it goes back towards right. Okay, so in this whole process, here the acceleration again increases and the speed decreases, acceleration decreases, speed increases. Okay, and this motion keeps on continuing throughout the whole life. Okay, because there is no loss of energy, no loss of energy. Okay, so we will begin our chapter considering that there is no loss of mechanical energy in the motion. Then only a continued simple harmonic motion with constant amplitude will take place. Otherwise the amplitude will keep on decreasing and it will look like a damped oscillation, which we will study later, but not now. Fine. So this is the absurd way of understanding SHM. I mean, if anyone tells you SHM, you just need to remember that the motion is something like this. Okay, and where the velocity decreases or increases, how the acceleration is changing, like this. We'll discuss these things in our future lectures in more detailed way, but you need to visualize the whole thing in a more so that you can remember or you can recollect all those things in the examination hall. Okay. Sorry. Fine. Now next is what? Okay, we know that a particle will perform simple harmonic motion when a force of F equals minus kx is acting on it. Okay, now we know then the acceleration would looks like omega square x, where omega is the angular frequency, which is equal to k by m. And we are more interested in finding out how the position of the particle changes with time. So we have A equals v dv dx minus omega square x, so v dv equals minus omega square x dx. Sorry. Okay, so let us check the motion once again. This is the mean position. Okay, this is the amplitude, this is the negative amplitude. We know that when x is a, that means when the particle reaches any one of its amplitude, the velocity becomes 0. Fine, and at any position x, the velocity of the particle is v. Okay, so finally v square by 2 equals minus omega square x square minus a square. So finally we are getting omega square times a square minus x square. So this is how the speed of the particle varies with the displacement. Fine. Okay, so as you can see, when x equals 0, v is v maximum and it becomes omega times a. So the maximum speed of the particle is when it is in its mean position, and the value is omega times a, and when it is in its extreme position, the velocity becomes 0. Fine. So this is how the velocity or the speed varies with displacement. Now let us understand one thing, that SHM can be of numerous types. Okay, it can be of n number of n types of amplitudes, means amplitude can be anything. Okay, and amplitude is directly related to its energy. Okay, amplitude is directly related to the energy of the particle. So first you need to fix the energy of the particle so that you can fix the amplitude of the motion. Fine. So first let us fix the amplitude. Okay, we have fixed the amplitude of the motion. Now another thing, to reach this position, it's not mandatory that you need to throw the particle from x equals to 0. You can also throw the particle from some x equals x naught in this direction. Okay, that means to reach the amplitude A, or to perform an SHM of amplitude A, it's not necessary that you need to throw the particle from x equals to 0. You can throw the particle from anywhere and in any direction. I mean, of course, the position and the speed must balance each other, or must be suitable, so that it reaches till x equals to a, it does not go further a. Fine. So, but what I am trying to say, that even if you fix the total mechanical energy, that means even if you fix the amplitude of the SHM, there can be infinite number of further solutions, because starting point and direction of velocity can have infinite combinations. Okay, so let us take one such combination where the particle starts from x equals x naught and the velocity is towards the positive direction. Okay, so we have v square equals omega square times a square minus x square. So v equals omega root over a square minus x square. Okay, fine. And v is rate of change of displacement. Okay. So dx divided by root over a square minus x square equals omega dt. So if you integrate both sides at t equals to 0, x equals x naught, because this is our boundary condition, initial condition, to, as we know that SHM have infinite number of solution. Out of those infinite number of solution, we need to get one perfect solution. Okay, so what we are getting right now is a general solution. Okay, we won't get an perfect solution. Okay, for getting a perfect solution, initial conditions must be specified, and we'll check all those things in our future videos. Okay, at any time t, the position of the particle is x from the mean position. So integration of left hand side is sine inverse x by a with the lower limit x naught, upper limit x. Okay, so this one is sine inverse x by a minus sine inverse x naught by a equals omega t. So rearranging everything from left hand side to right hand side, we have a sine omega t plus sine inverse x naught by a. Okay, now few intellectuals try to rename this thing as phase constant or phi. So our final general solution for simple harmonic motion of a particle would look something like this. So this is our general solution. Fine. So this is what is the foundation or the building block of this chapter, this variation of the position with time. Okay, now let me go through this, what we have done actually. Let me go through this whole section once again. Let us recap the whole thing again. So basically we have acceleration, okay, which varies like this. Okay, and we know when the acceleration of a particle varies in this way, its motion would look something like this. How its velocity or speed or acceleration will change, we know in a qualitative way. Okay, now we know another thing. If the acceleration varies like this, the speed would vary something like this. Okay, now as you can see that you need, for getting A, you need to fix the energy of the SHM. That first fix the energy of the motion of the particle, or for the particle that is performing SHM. So first, in this case, the energy is fixed, because without fixing the energy you won't get a specific amplitude. Okay, fine, the energy is fixed. That means the particle would go from plus a to minus a. Now here's the catch, that for the particle to reach till x equals a, it's not necessary that the particle should start from the mean position. The particle start from any other point, here or any other point. Suppose the particle wants to start from x equals x naught, okay, and the particle is being thrown towards the positive direction. Of course, the velocity must be suitable, must be arranged in such a way that it won't go further x equals a. Fine. So there can be infinite number of initial conditions, or you can say initial boundary condition, to reach x and to perform this kind of SHM. Okay, so energy is fixed, but still we have infinite number of solution because the initial condition is not fixed. So now we need to fix the initial condition that at t equals to 0 the particle starts from x naught, okay, and the velocity is either positive or negative or anything. From there we get another thing, that is sine inverse x naught by a, which we renamed it as phase constant. Okay, so out of all the infinite solution we get a perfect solution, that is this one, x equals a sine omega t plus phi. Fine. So phi depends on the initial boundary condition that is given by the examiner or anything. So let us do one example. From there we can understand what is the importance of phi. Okay, suppose in our question it is said that the particle is performing simple harmonic motion and it is following a relation of a sine omega t plus phi. Okay, at t equals to 0 the particle starts from x equals a by 2 and the velocity is positive. That means at t equals to 0 particle is at x equals a by 2 and the velocity is positive. Okay, fine. Now just put t equals to 0 here and x equals to a by 2. So we have sine phi equals to half. So as you know that the graph of sine looks something like this. For half there can be two values of phi. One would be half pi by 6 and pi minus pi by 6, that is 5 pi by 6. Okay, so we have two values of phi. Now you must be thinking which one of these two values would be our correct value of phi. So for that we need to check the velocity. As you can see that the velocity is in the positive direction, and basically for getting velocity you just need to see the slope of this graph. Fine. As you can see at pi by 6 the slope is positive, and at phi equals 5 pi by 6 the slope is negative, and slope of this graph will represent the velocity, and velocity is positive here, and at pi by 6 the slope is positive, so the final answer will be pi by 6. Okay, so out of all the infinite solution, our final solution would look something like this. Fine. Let us take another example and let's just solve it very quickly. At t equals 0 the particle is at x equals minus root 3 by 2a and v is positive. We need to find out the value of phi. Okay, so let's just quickly write down the general solution. T equals 0, so this is root 3 by 2 sine phi. So let us draw the graph here. Okay, so minus root 3 by 2, you have pi plus pi by 3, that is 4 pi by 3, and 2 pi minus pi by 3, that is 6, 5 pi by 3. Okay, so out of these two values you can see that velocity must be positive, that means the slope must be positive. The slope here it is positive. Okay, so final answer would be 5 pi by 3. Okay, so positive slope, 2 pi minus pi by 3, that is 6 minus 1, 5 pi by 3. Okay, fine. So these are all the basic relations which you need to know for the start of this chapter. I'll be continuing this lecture series, okay, and in the next video we'll be discussing more about phasor diagrams and initial boundary conditions. Okay, so I hope I will see you all in our next video, and if you like this, if you want this lecture series to be continued, please do subscribe if you are new to this channel, and just like the video, show some support, be a good person. I hope you become an IITian. Okay, thank you very much. Goodbye.